record, share screen. Okay, select that one and share it. Okay, you see my screen?
Let me see.
It's showing
Yeah, I see it now.
the questions.
Yeah.
Okay, I'm going to record this. It's recording. We're going to work all the problems in assignment 7, and then I can post that for the class. So here we go. Question 1. And again, my goal is not to get into lengthy explanation. So we can.
We got to question 4 yesterday. Remember we did the
You
first
want to
3s?
start there? Well, let me just review these for the class real quick, okay?
Oh, okay. That's fine.
Yeah, but yeah, I appreciate what you're saying. Yeah, it makes sense. Hypotheses are always statements about which of the following. Okay, so hypotheses are always statements about population parameters. That's what
Just to tell you, it's not showing in the screen again.
it's not showing it. Okay,
Yeah.
all right. Let me. Yeah, thanks for letting me know. Let's try again here. Let's try this one and here.
Yeah, there we go.
Okay, good deal. Okay, so hypotheses are always statements about population parameters. Okay, so next question. I guess that's it for that question, maybe. Okay, which of the following is measured by a test statistic? Okay, the test statistic measures how far away the observed mean lies from the hypothesized value of the population mean. So the hypothesized value is what we call the null hypothesis value. It's the status quo or the claim. That's the hypothesis value, and it's of a population mean. Our test statistic comes from the sample, right? And so it's a number. It's actually counts the number of standard errors away from the proposed population mean we are. That's what it does. So it measures how far the observed mean, which is your, if we're doing means testing, this would be X bar, how far X bar is from your null hypothesis mean. That's what this test statistic does. So next. Okay, here we have a random sample of 10 healthy people with body temperatures. Test the hypothesis that the population mean is not 98.6 at a significance level of 0.05. So we're testing that it is not this value. So our alternative hypothesis is going to be not equal to, okay. It's not showing me part A here in this problem. Let's see. There we go. Let's get up here. Okay, which of the following correctly states the null hypothesis H sub O and the alternative hypothesis H sub A? Okay, and C does, because the null is that it is 98.6. The alternative is it is not 98.6, which means it's not equal to 98.6. Okay. Step 2, a stem plot's prepared. Okay, and a stem plot shows you of the data. We had a data point that had a temperature of 96.8. So this is one data point. It was 96.8. We had a data point that was 97.2. We had another data point that was 97.9. etc. So for at 98 degrees, we had 5 different data points that were 98 point something. Okay, one of them is 0.1, another 0.2, another 0.4. That's how you do stem plots. Great tool. You don't need a computer. You can write that down very fast. And if you look at it sideways, it's the shape of the histogram, right? It's just you have a little more information than what's in a histogram because you have the actual value of each point. when you put the last digit with the first two, you get the actual value of each point. So a lot of information in a nice picture you get real fast in a stem plot. Comment on data collection. Okay, the sample is random and observations are independent. It told us that in the problem here. Okay, that's important. We're going to use a one sample t-test. So all these individual x's comprise one single x bar. So this is one sample. Okay, and the fact that n is less than 25 means this is considered a small sample. So we have to use the t distribution instead of the z because we have a small sample. So we're using a one sample t-test. Significance level, this is also known as the type 1 error rate. Okay, alpha equals 0.05. That's our significance level. Once again, also known as type 1 error rate. And that's it for that. So step 3 says compute the test statistic. Okay, so I'm going to compute it. I've got to go into another screen and then share that with you. So I'm going to open up StatCrunch. Let's see, there's an icon here. Well, actually, I'm not going to open it for this one, okay, because it's already done this report for us. We want to get through all these problems, so we'll just use this and not show you 2 other ways you could do the same thing, all right? But it gives us this report. You run StatCrunch, and it gave us this t here is the test statistic, okay, and its value is minus 1.43. Other important thing from this was a one sample t-test, so that the outcomes from this, if you will, are these values here towards the end. The t, which is the test statistic, this is the t-score for our sample. It's how many standard errors our sample is away from the proposed mean. And this tells you what the standard error is. So this is the size of the standard error. This is how wide one standard deviation is. We're talking about standard deviations of x bar, which is okay, and the distribution of x bars is called the sampling distribution. So we're minus 1.43, so we're 1.43 standard errors below the null mean that was proposed. And the p-value for this test, which means this is the probability of getting this or a value that's even further away from the proposed mean. That's what the p-value is. Probability that you would if you randomly get a sample, you'll get a sample that had the t value that you got, or you'll get a sample more extreme than that. So more extreme than this would be further away from the mean. Okay, since this point is below the mean, more extreme would be, it would be a negative number that's bigger than 1.43. For example, minus 3 point something. That's a more extreme value, okay? Since it's a two-tail test, though, also keep in mind more extreme could be a number that is bigger than positive 1.43 also, right? It can be out in either tail. So it's saying the probability that you got something bigger than a plus 1.43 and also the together with, I guess you would say, the probability you got something greater than plus 1.43 for a t-value, or you got something less than minus 1.43. Those two probabilities together make up this probability. It's the probability of getting a sample as extreme, as far away from the mean as what you got. Okay, so that's enough about that. Done. We just wrote the p-value from that report, the t-value from the report in there. Okay, and then we scroll down, interpret. Okay, are we going to reject or not reject? There's 2 ways to look at this. One is you can compare your t-value with the critical t. That would be known as t star, right? And T star we either get from a table or from technology. And we don't have T star right in front of us right now to see what that number is. Okay, we could look it up from the significance level. So let's do that because we can do that quick here. I have to share the screen again, but I'm going to go back into StatCrunch, and we want to get we want to know what T star, what's a critical T we're going to compare this against. Okay, our sample size is 10. We need to know that. So let's go into StatCrunch. Open in StatCrunch. Okay, now I want to share, so I have to stop share, pick StatCrunch, reshare. Should be able to see it. We go Stat, Calculators. We're going to use a T. So this is T distributions here, this calculator, okay? T distribution. And this was a two-tailed test. So we're going to say between, and we want the critical T for significance level of 0.05. Okay, so we have to put our degrees of freedom in, and we had our sample size was 10, so degrees of freedom will be 9. It's always sample size n minus 1 is degrees of freedom. At 5, at alpha equals 0.05 significance level, that means our probability is 0.95. Okay, we're testing at a 95% confidence level. Hit compute. So these are our critical T values for this test. So this positive number would be here on the graph. That's T star, okay? That's your upper threshold, if you will, for your test. So that's the number we would be comparing our sample T, our test statistic T comes from the sample. We compare that with this critical value of T here in order to determine whether to reject or not. And the rule is if your sample T is more extreme than your T star, you reject. So extreme means it's bigger than it. It's further out in this tail. So it would be, your sample T would have to be above 2.2622, or it would have to be below negative 2.2622 to reject. Okay, so that's that's that. Let's see if I can go back here to the question. I think I have to reshare again to see it. Share, select, reshare. Okay, so is it going to let me scroll? I have to click in it. I can scroll. Okay. Do we reject or not reject? We saw, and I've already forgotten what it was. I know it was 2 point something, right? So this number, negative 1.3, is not lower than negative 2 point something, okay? So we would not reject based on this T value because that was like 2 point, I think it was, maybe I can see that again. Maybe it's, no, I was thinking it was still up there. Is it up down here? No, that's not it either. Okay, get out of that. Let's go back. Now I've completely lost the screens. Let's go here, there. Okay, I had another there. Okay, so you can't see it, but I'm looking at that T calculator, and it's 2.2622. That's the actual value, 2.2622. So going back to the question, I don't know why it's got the question is gone now. There. Okay, maybe you saw that the whole time. I couldn't see it. So the T star was 2.2 something again. Okay, and it's symmetric, so that means you have another one in the other tail of minus 2.2 whatever. Well, this is not below the minus 2.2. It's just minus 1.4. So you do not reject. You can also see that from the p-value, okay? P-value is 0.188. We compare that to our significance level, which in this problem was 0.05, okay? If this probability is smaller than your significance level, you reject. If it's not smaller than your significance level, you do not reject, okay? So 0.1188, we're bigger than this, so we're not as far out in the tail as this is, so we do not reject. At this significance level, we do not reject. And this significance level, 0.05, same thing as 95% confidence interval. So let's look at the questions and answer them. We do not reject. There's two of these that say do not reject. And this one says we're not rejecting it. Population mean is definitely 98.6. Wrong. Just because we don't reject it, that just means that it could actually be 98.6. But we don't know exactly what it is, okay? We cannot reject it. That's all this says is we cannot reject 98.6 from the data at the 0.05 level. That's correct. So do not reject. But we cannot say that the population mean is definitely that value. So B is the right answer. Let's continue on here. It's not letting me scroll. Why is that? Oh, I have to hit next here, I guess. Okay, new problem. Let's put this in StatCrunch. It says make a graph, describe its shape. So we got to make a graph and see which one of these is the closest to it. So we'll put the data in StatCrunch, and then I'll share after I just pulled the table up. I'm transferring it to StatCrunch. Okay, now I want to share this. In order to share, you got to stop sharing. Okay, and then select StatCrunch and reshare. There, should be able to see it. Yeah. Okay, so it just wants a graph. So we go graph, and those were histograms that we were looking at. So we're going to make a histogram. We have to tell it the data's in column 1. We're done. Say compute. There's our histogram. And now we should be able to go back. Let me see if I just minimize this, what happens, if it'll let me. Well, I think I have to say stop share. Then it wipes everything out and hit share again. I have to go back to that. Boy, that's a lot of rigmarole. So I guess I can maybe minimize this before to go back to the other. Let me see if it'll let me minimize it. Yes, that's good. I think I'll be able to pull that back up now, but I have to reshare here. So I'm going to get rid of this little guy too. I want to reshare this screen. So stop share. And reshare the screen, and we have this. Okay, and it says which one of these looks more like what we had. I'm going to look at it again. Okay, there's what we had. Actually, it looks a little bit different than all of these. Well, that's not helpful there. Where did it go? Did it close it? Okay, yeah, it looked like, looked more like D, I believe. I wish that, maybe it's still there. No, that's something else. I'm gonna pull it up again one last time because it doesn't actually look exactly like any of these pictures. And I'm guessing it's because the bins widths are a little bit different, so it has a slightly different shape. Click the icon to view the table. Okay, put it in StatCrunch. Make a graph. I think actually you don't have to see this. I'm just doing what I did before. So I'm making a histogram. Select it, compute it. Let's see what we got. Yeah, this graph actually doesn't look super similar to it. Okay. Can I just minimize this part and the graph tab? No, the graph goes away. Shoot. Well, I've got the table here. I don't know if do you see this table, or do
Yeah, I
you
see the table.
you see a table moving around?
Yeah.
Okay, well maybe we can look at the table. I think it looks like it's either this one or this one, but I can't have them on the screen at the same time. But we can decide that real easy. Let's look at we have a big spike here at very low values. So in the table, and that these numbers look like they're 4 or below. We got a whole bunch of them. We got 12, 13 numbers 4 or below there. Okay. And if we look in this table, yeah, we don't have anything like that here. There's nowhere near that many. So it's not A, so it must be D. This looks kind of close to what that histogram that we generated was. So let's say D and check answer. Yay. All right. Okay, the distribution is, we'll pick from the choices here. This one is slightly skewed to the right, okay? Slightly skewed to the right. So see how it's got this downward slope. It's not really a normal shape because this one's too tall to be all the way close to the left-hand side. So
Yeah.
it's slightly skewed to the right, okay? Now, what that's telling us is the whole point of this is to say we really don't have a nice normal distribution here from what we can see in our sample. So we can't say the population's normal because this is skewed a little bit. That's the takeaway from this, that the population's not normal because this is skewed. If this column were over one more division, then it would be a reasonable approximation, but it's not. So population is not normal is what we get from this. Okay, the other key thing here is that our sample size is 40. Well, that's a quote unquote large sample. It's more than 25. So these two things together, not a normal population, but we do have a large sample, tells us we're allowed to use the t distribution, okay? We're allowed to use t because we have a large sample and the population is not normal. So let's continue on here. Check answer. Okay. Minimize that. Find, report, and interpret a 95% confidence interval for the population mean, okay? We can calculate that in StatCrunch. So let me go up here to, I'm just trying to get a little more room. I guess I got to click this again. We're going to get a 95% confidence interval on the population mean, okay? So I'll put it in StatCrunch. Stop share, share, select, reshare. Okay, 95% confidence interval. We know we're using a t-test also, right? So we go to t-stats. It's a t-test because we don't have a normal population, so we cannot use z. We did have a large sample, so we're allowed to use t even though the population is not normal. It's one sample. We have the data. Okay, we select column 1. And right now we just wanted a confidence interval. So we can just click that and it'll give it to us. Now we can go down here and we can tell it it's going to give us, we can get that plot too, if we want it. And we'll say compute. That'll give us our confidence interval here. Okay. And, okay, we can see it there. So here's our confidence interval, lower limit. I'll write this down. I've got 7.95596. I'll take that to 4 digits, okay? 7.9560 would be 4 digits, okay? Yes. All right, and then the upper limit is 10.8440. That's the upper limit for our 90% confidence. We could go ahead and write the standard error down. We may need it later. I don't know if we do or not. I'm going to write it down. Standard error 0.7139. Okay. Oh, and it says the sample mean there is 9.4. Anyway, it just wanted a confidence interval. We have it here, lower and upper limit. So let's go back to the problem. And it wants 2 decimal places. Okay, so that's 7.96, 7.962, and this would be 10.84. And we say check answer. It likes it. We move on. Interpret the interval. If the sample were repeated many times, in other words, you go get a sample many times, 95% of all confidence intervals would contain the true population mean reaction distance, okay? That sounds pretty good.
It's not showing the questions, by the way.
Oh, it's not showing them? Okay, all right, let's go back here. Okay, so I typed the confidence interval in there. So if we sample many times, and each time we do that, we calculate a confidence interval, right? Because we get a different X bar and maybe a slightly different sample standard deviation each time we do that. So each time we do it, we calculate a confidence interval. We do that many times. 95% of all those confidence intervals would contain the true population mean parameter. Here it's a reaction distance. So that's the answer, A. That's the correct interpretation. Okay. This is, suppose a professor said the population mean should be 10 centimeters. Test the hypothesis that it's not 10. So our null hypothesis HO is that mu equals 10 centimeters, or we could call that mu sub naught. And our alternative hypothesis is mu sub naught is not equal to 10. So that means it's a two-sided test, okay? A two-tailed test. And it said tested at the significance level of 0.05. Determine the null and the alternative. So the null, we got to find mu equals 10. The alternative is mu is not equal to 10. And that's down here in F. Okay. Check answer. We're good there. Okay. The test statistic is, it wants to know the value of the test statistic. Okay. Remember we said it was a t-test. Okay. And we got our data here. Let's see. Put it in StatCrunch. Or did I write that down already? Maybe not. Maybe that was another. Okay, we want the test statistic. We know it's a t statistic, right? So we're going to say t-stats, one sample. We do have the data. We got the individual x points for this sample. So there, we want that. Let's go ahead and to get the t-stat, and I made this mistake this morning, okay? I don't want to make it again. We're not doing a hypothesis test in order to get the t-stat. This part of the problem, we just want to know what that number is. So we're not doing the test to get that number. But that number, okay, the formula for the test statistic t is t equals, and we're doing means testing here. So it's x bar minus mu sub naught, which is the null hypothesis for the mean for the population. So our sample mean minus our proposed population mean. That quantity divided by the standard error is our test statistic t, okay? Well, in order for the software to know what our null hypothesis was, even though we're not really doing a null hypothesis here per se, we're just trying to get the, or we're not doing a hypothesis test. We're just after, we want to know what the t-value is to answer this question. Well, you can run a hypothesis test and it'll generate the t. So to run it, we have to put the population parameter in, which I believe it said was 10, right? And so, in other words, yeah, because the formula for the test statistic is x bar minus mu sub naught over standard error. If we don't tell it what mu sub naught is somewhere, then the software doesn't know what it is. So when it computes it, it's going to have a wrong value. Okay, so but you act as if you're doing the complete hypothesis test here in this software, and you tell it what the null value is. Now it'll have that value, and we'll get the value of our test statistic this way. So we hit compute. Here's our test statistic now. I'll write that down. So t equals minus 0.8404, and it gives us a p-value. And p-value is 0.4058. Okay, that's all we need from there. It gives us the standard error. That's nice to have, and the degrees of freedom. But let's go back to the problem. And now I got to share it again. Reshare, or select it. Reshare. Okay, let's minimize that. Wants to know to 2 decimal places, what's the value of t? It's minus 0.84. Okay, so enter, likes that. Wants to know p, that same hypothesis test we just ran gave us p 0.4058. I think I'll do a separate video. I mentioned lots of these things in the same video, but I think I'll break it out and just do a real short one and say, hey people, here's what a p-value is and what it means, okay? So I'll do a short video that explains what p-value is. But what all you need to know about p-value is when you're doing your hypothesis test, you're going to compare the p-value with the alpha level, right? The alpha was a significance level. Usually it's 0.05. If you're doing the 95% confidence level, alpha is 0.05. So when you're doing the test, you compare your p-value with the 0.05. If your p-value is less than 0.05, you reject the null. If it's not less than 0.05, you do not reject. So that's what p-value is good for. And you can get that same kind of information just by looking at this test statistic. If you know what your t star was, and for us it was 2.2 something. Well, no, for this, what was it? No, for, well, we didn't calculate it. We didn't determine t star. We didn't look it up yet. Okay, we could do that. But you compare your test statistic with t star, and if the test statistic is more extreme than t star, then you reject the null. And more extreme means further away from the proposed mean, okay? So here, since our test statistic's a negative number, we would use negative t star. So whatever the value of t star is, we have negative that value. And if this value is less than that, so it'd be a bigger negative number than the negative t star, we reject. Or if this wasn't a negative number, had we gotten a positive number for the test statistic, then we would just compare that to positive t star, and you say if it's bigger than t star, you reject. So in either case, if the test statistic number is bigger, when I say bigger, I mean a larger magnitude than the t star or the minus t star number, you reject it. So it has to be less than the negative t star or greater than the positive t star, right? You reject. So that's one way of doing the test. Or look at the p-value and say, is the p-value less than alpha? If it is, you reject. If it's not, you don't. So check answer. Oh, it says round to 3 almost. I've got that wrong a bunch of times before. It says round to 3 decimal places. So there. Now check answer. Okay. All right, interpret results. The p-value is, it's greater than our alpha. We were testing at the 0.05 significance level, okay? So this p is greater than 0.05. So since the p-value is greater than alpha, we do not reject. I mean, a p-value is the probability that you'll get a sample that's as far away from the mean as what your sample is, or even farther from the mean than that, okay? That's what the p-value means. By chance, the probability that a random sample will be at least as far from the mean as your sample was, if the null hypothesis is true, or under the condition that your null hypothesis is true. So this says there's a high probability that you'll get a value like what you got just by chance, if that's true. So you cannot reject it, okay? And here, so we do not reject, so there is going to be insufficient evidence to conclude that the mean is different from 10, from the null value. So we don't have sufficient statistical evidence to reject it, okay, at the 0.05 level, because your t star value changes with, you know, for every different alpha level, you have a different t star value, which is the same thing as saying for every different confidence level, you have a different t star value. So at this particular confidence level, which is 95%, there's insufficient evidence to reject it. There may be enough evidence to reject at a different, at say a 90%, it might be rejected at 90% and not be rejected at 95, and then it would not be rejected at 99. So it depends on your confidence level. Your threshold changes, or what you use to compare against changes depending on your confidence level. So you always have to state that in your results, that you were testing at this significance level. And when you test at this level, we don't reject, and there's insufficient evidence to reject. So, okay. Next question. All right, the weights of 4 randomly selected bags of potatoes that are labeled 20 pounds, and here's the weights. Assume normality. Okay, so once again, we have a small sample size, but our population is normal. Okay, but here we got a normal population, but because we have a small sample size, we have to use the t-distribution. We can't use z when we have n is less than or equal to 25, okay? And n here is 4. So it says, part A, where's the question at? I got to scroll up or something because, oh, here it is, way up here. Using a two-sided alternative, should you be able to reject the hypothesis that the population mean is 20 pounds using a significance level of 0.05? Well, we don't know yet. We haven't done the calculations, right? But the rest of this question goes on to say, why or why not? And then they tell us, well, here's your confidence interval, okay? So they're giving us the confidence interval. Well, now we have enough information to decide. We have the confidence interval, which is a 95% confidence interval. Okay, and we know that the proposed or the null value is 20. That's what we're testing. Can we reject the notion that the population mean is 20 based on this confidence interval at 95% confidence? So you ask yourself, does the confidence interval contain the value or not? And you look there and you say, no, 20 doesn't fit inside this interval. Since it's not in the interval, you're going to reject it, okay? So we reject, and 2 of these answers say reject. It says because the interval does not contain the proposed mean. So reject it because this interval does not contain 20, what we're testing. That's true. That's what we want. So check answer. Good deal. We move on. Okay, determine the null and the alternative hypothesis. So the null is going to be mu equal 20, and the alternative hypothesis, we got to go read it. It says using a two-sided alternative hypothesis. So it's telling us this is a two-tailed test. So that means we don't know what it is. We just want to know if it's different from 20. It could be bigger than 20, could be less than 20. Because of that, we have to test on both sides of it. So our alternative hypothesis is stated that mu is not equal to 20 because we don't know. It could be bigger or smaller. And this is saying we're testing for either one of those possibilities. So the null is 20. The alternative says mu is not equal to 20. Two-sided test. Check answer. That's right. Next question says, what is the test statistic? So we got to get t, the t value. And we did this before for the other problem. Okay, so we'll go into StatCrunch. Well, let me transfer this data into StatCrunch here. There we go. Wants to know what's t for this data, and the formula for t. Go out here to the camera. Okay, I think I can go back and forth. Maybe, yeah. Stop share. Yeah, select that. I thought it made that big. There. Okay. The formula for the test statistic. So ignore this stuff up here. Test statistic. Okay, is t equals x bar, our sample mean, minus our proposed population mean, the mean for the null hypothesis. What we're saying that is that value divided by the standard error. Okay, standard error of means. All right, that's how you get. You could just take that data. It's just 4 data points. Get the average, subtract what it said. It said 20 pounds is how they're labeled. They're supposed to be 20. That's what we're testing. So you get the the mean, the average for your sample, subtract 20 from it, divide by the standard error. The standard error for means is S over square root of n. So S is the standard deviation inside that single sample. We take those 4 values and compute the standard deviation for them, divide by the square root of n, which was 4. So this would be dividing by 2. Gives us this standard error, which is how big the standard deviation of the X bars is. So T is a measure of how many standard errors this difference from the mean is, or our distance from the proposed mean, how many standard errors away from the proposed mean is our sample. That's what this does for us. It gives us a number. So this is like a t-score. It's a number of standard deviation units, and actually those are standard error units. And this thing tells you how big a single standard error is, how wide it is, right? So when you have your here I am explaining, can't help myself. When you have this is 0, this is 1, 2, -1, -2. So the standard error is how wide that is, because this 1 means 1 standard error away, which is like 1 standard deviation away from the mean, 2 standard deviations away. So that's all that stuff, okay? Let's go back to StatCrunch and share it. Okay, and we want the test statistics, so let's go T, or stat. We're doing T stats. It's 1 sample. We have the data. We click there, we select it. And once again, here, if we want to know what the test statistic is, we could calculate it with that formula that I showed you, right? So you could just plug that in a calculator and get it. But the software, when it runs a hypothesis test, it has to calculate it. So we can tell this to run a hypothesis test, and we have to if we want to get T out of this screen, because otherwise the software does not know what mu is. If we just say, like if we just tell it to give us a confidence interval, we don't, well, let's tell it to do that, and let's see what happens here, okay? See, notice we don't have any T statistic. We just get the interval. That's what we asked for, and we get it, right? But going back, our question's asking, what is the test statistic T? What is its value? So to get its value, one sample with data, we select it. We're gonna tell it a hypothesis test, because this is how we can tell a software, here's the value that you need for mu sub naught, the population null. We're going to put it in here, and it needs that in order to calculate what T is. So ordinarily, you just be doing this to run the hypothesis test, and it just so happens that the test statistic T is one of the values it gives you when it does the hypothesis test. But we're kind of using this backwards here. We're using it so it can tell us what T is. I'm going to move this over because I've forgotten in this problem what mu sub naught was. Was it 10? Is it? No, these are pounds of potatoes. Okay, so 20 is mu sub naught. We're doing bags of potatoes here. So this null hypothesis value for the population mean, the proposed value is 20. So we say compute, and here's our t-stat. Now see how big that number is? 9.3157. That's a huge number. Okay, think in terms of standard deviations. Remember, 99.7% of all the data will be within plus or minus 3 standard deviations. This is saying 9 standard errors away. And the standard error is the standard deviation of the X bars, right, of the sample means. So we're a huge way away from the proposed mean in our sample here. And also look at the p-value. It's very small, right? We're going to, if we're testing at the 0.05 significance level, we compare this number to 0.05. If it's bigger than 0.05, we cannot reject. If it's smaller than 0.05, we do reject. Well, this is a lot smaller than 0.05, so we're going to reject based on that. But we would know just from looking at this t-value, we're going to reject because this is many standard errors away from the mean, right? So it's a very low probability that you'd get this by chance. So we're going to say, nah, that proposed mean is most likely wrong. We're going to reject that we think that's what the value is. So let me write these down. I got the t and the p is 0.0026. Let's go back to the problem. I think I gotta change the share again. Reshare, yada yada, select it. And there, okay, you should be able to see it. The test statistic, it wants it to 2 decimal places. And so that's 9.32. 9.32. Okay, it likes that. The p-value that we got is 0.0026. Oh, how many decimals it wants? It wants 3, so 0.003. Okay, it likes that. Okay, choose the correct conclusion. And once again, we have a very small p-value, much less than 0.05. So we reject the population mean of 20 pounds. End of story there. Okay, next question. Health agency suggested a total cholesterol measurement should be 200 milligrams per deciliter or less. Records from 50 randomly and independently selected people from a study showed results given below. So here's a report. They've already ran this data. Determine the null and alternative hypothesis. It says test the hypothesis that the mean is more than 200. So we have reason to suspect that the real value is more than 200. So our null is going to be that it is 200. The alternative is going to be that it's greater than 200. So that would be here, D. Check answer, we're good, we move on. The test statistic is, and they've already given us that, and it says type an integer or decimal. So do not round, so 1.35. It gave us the test statistic right here in this report. Okay. The p-value, it gave us that. It wants, and it says do not round, so we just report it. So that's 0.092. Didn't take the two there. Okay, good. Interpret the results. Since the p-value is less than or equal to the significance level, it's, or wait a minute, I'm sorry. This p-value, oh, this is a different problem. I'm still thinking about the potatoes. Okay. This p-value is greater than the significance level, 0.05, okay? Change that, greater than the significance level, okay? Since the p-value is greater than 0.05, we do not reject, okay? Because we're saying we have to be below this probability on our sample before we can reject the null and say that's a very, very rare event. We're going to reject. We got to be below this probability. We're above that probability. It's not real high, but it's above our threshold. It's above our trigger level, so we can't reject. There is insufficient evidence to conclude that there's more than, because we cannot reject, so we don't have evidence to conclude that the alternative is true. We don't have evidence to reject, basically. Okay, so next question. In a country A, population mean height for 3-year-olds is 38 inches. Here's a random sample of 15 3-year-olds, so n equals 15 from country B, showed a sample mean of 37.2 inches with a standard deviation of 3. Boys were independently sampled, assume heights are normally distributed in the population. Determine whether the population mean for country B boys is significantly different than country A. And we're testing at a significance level of 0.05. So that is at the 95% confidence level. We want to say the question is country B significantly different than country A? We got 37.2 as our sample from B. And we know that the whole population of A is 38. And we're also given the standard deviation. This is a standard deviation. This is a sample standard deviation of 3 inches, okay? So let's continue because we don't have any answers to choose from here. Okay, which of the following correctly states the hypothesis? Okay, the hypothesis is you're testing to see if country B is the same as country A. So the null value for the mean, the claim would be, we're checking to see if country B is 38 inches. So we look for mu equal 38. We've got it in 3 places here. The alternative is, okay, it says determine whether the population is significantly different from A using this level. That's all it says. So what we're testing then is that if country B is not equal to this. It just says significantly different. There's no mention of whether it's higher or lower. So we don't know. We're just testing to see, is it different, period. So it's a two-sided test. So that's going to be, the alternative hypothesis is going to be not equal to 38. Is it different from 38? Is it not equal to 38? So there. Okay. Find the test statistic, okay? We got 15 3-year-olds. Here's the sample mean, and here is the sample standard deviation. So here, T, we go back to our formula for T, and T equals X bar minus mu sub naught over the standard error, okay? And I'll plug these in from our problem here, and then I'll switch the camera to this. So our sample mean, X bar, was 37.2. The mean that we're testing to see if country B is the same as country A, which is 38. So 38 is the null hypothesis. And standard error, remember we said it's S over the square root of N. Well, they gave us S in this problem, 3 inches. So it's 3 over the square root of N. N is 15. There were 15 boys that were tested. So let me write that down here. Standard error equals S over the square root of N equals 3 over square root, it's 3 inches, of 15. So switch it to the, so you can see that. And turn it. Okay, so here's our test statistic. Sample mean and the proposed population mean that we're testing divided by standard error. Standard error is the sample standard deviation divided by square root of n. That's 3 over square root of 15. So let me punch that in the calculator here. 3 divided by the square root of 15 equals, so standard error of x bars equals 0.7746 to 4 digits, okay? So 0.7746. So I just do this, punch that in the calculator, 37.7 minus 38 equals, divided by 0.7746 equals, and we get t equals negative 0.3873. You got all this, Ruben?
Yeah, I'm plugging everything in the calculator right now.
Okay, just checking. Good deal. All right, so we've got t. That's what the problem asks for. Let's go back to the problem. All right, and t equals, it wants 2 decimal places, so that'd be minus 0.39, minus 0.39, enter. Oops, it doesn't like that. So what did I do wrong here? I got through. This is what I did, so why doesn't it like it? Oh, I didn't, where did I get x? No, that's right, that's x bar. Oh, maybe I used the wrong. No, that's the right end. Okay. Why doesn't it like that? It says, typing it rounded to 2 decimal places that as needed. Okay, so I need to redo this calculation here. We got 37.2 minus 38. Okay, so that's negative 0.8, right? Negative 0.8 divided by the standard error divided by 0.7746. Oh yeah, I don't know, that t I got doesn't look right for some reason. What did I do wrong there? I think I just punched something wrong here, so let me do it again. 37.2 minus 38 equals negative 0.8, that's right, divided by standard error 0.7746 equals, oh, okay, yeah, I punched it in wrong somehow. Not sure what I did. Punched it in wrong. Okay. The t that I get is minus 1 point, and it wants 2 decimal places, so that'd just be 0.3. Okay.
Mine was wrong too, but I just forgot my negative.
Oh, okay.
Yeah.
Yeah. All right. So, and we notice, we can just look right there. So remember, this is how many standard errors you are away from the proposed null, right? And we're below it, but we're only 1 below it. So if we're testing at an 0.5 level, we're not going to reject it. We already know that from this, okay? The t would have to be a much bigger number before we're going to reject. Okay, it says find the p-value. Okay, there's different ways to do this. Let's go into StatCrunch. And, well, I think, let's go into StatCrunch here. So, question, let me get back up above here. It doesn't let me scroll back up there. All right. 38, write this stuff down, 38, 37.2, and S is equal to 3. Okay, and we want the p-value. Well, all we need for the p-value actually is this test statistic. We can get p from just having this test statistic, okay? So we'll go into StatCrunch, and t that we need is minus 1.03. It says, what's the p-value for that? So that's asking, what's the probability that we'll get a value equal to minus 0.103 or more extreme than that, which means further away from the mean, further away from use of not than this is, okay? And when you say further away, since it's a two-tailed test, it can be on either side. So it can be a value that's less than negative 1.03, less being a bigger number, right? Like, for example, minus 3 point something. That's more extreme than minus 1.0, okay? Further distance from 0, right? Because the middle of the distribution is t equals 0. But it could also be a number that is greater than positive 1.03. That would be more extreme than that t value. And p is the probability, it's the area in both of those tails of getting that extreme number. So let me make the drawing here. Okay, and we have a t of minus 1.03. So the p-value is the probability that you get a value of t negative 1.03 or a value less than negative 1.03. So it'd be a bigger negative number. So that's the area in this tail. I'm going to switch the camera here. But the p-value also includes, this would be t equals positive 1.03. Okay, switch the camera. So a p-value means you get the, here's our t that we got, negative 1.03. So the p-value is this probability that's past this t-score. That's what p-value is. Probability of this area out here, okay? But since it's a two-sided test, since we were testing that it's not equal to, that means the p-value for this sample value, you actually have to add this probability also. Because we could have got a sample over here that had this t-value, right? And the probability of getting that or more than that is this area. And this area is the same value as this area. So you just find one of them and you double it, and that gives you the p-value. That's actually the probability that you're not inside that value from negative t to positive t. Well, you're looking at it, I see it backwards from the way you see it. My screen is reversed, but from this negative t, negative 1.03 to positive 1.03, there's a probability associated. And if we're well, this is a sample statistic here, okay? So for this sample, the probability that you would have got something at the mean or up to this value on either side is this area inside here. The p-value is the area in the tails outside.
Are you showing something in the screen? Because it still shows your paper. I'm not sure if you are.
Oh, yeah. Okay, my bad. Yeah, I got to change it again. Let's see. Let me say share. Oops, I don't know why it went to that. I did that. Where did that go? Stop share. I got to say stop share there. Oh, so you see the desk, the green desk, and pen and drawing now? Hello?
Yes.
Do you see the drawing now on the desk here?
Yeah, the drawing I do see it.
Okay, well that's just what I'm just talking about, this drawing. So
Okay.
so it said, what's the p-value? As it's asking. Well, we have a t-value, okay, and both of these are associated with your sample. All right. So this is a t-value for the sample. And what p-value is a probability that you get a value equal to that or more extreme than that. So that means anything further away from the mean than your sample is. So that's the probability in this tail out here, okay? But since it's a two-sided test, a value more extreme than this t-value would also be these values more extreme than this t was negative, so this is the positive t, so it's more extreme than that. It's saying the possibility that you get a t more extreme in either tail, so you have to add both of these probabilities together to get the p-value. But so that's what we're looking at, and we'll go into StatCrunch in the t calculator, and we'll just give it a t value, and that'll tell us. Well, actually, StatCrunch it'll give us this probability that's between these two, and then we subtract that from 1, and that gives us what this remaining probability is. So that gives us the p-value. If we get the probability between plus and minus t, we subtract it from 1, that tells us the probability that we're outside of t. Okay, so let's go back into StatCrunch. That should have brought StatCrunch up. I don't know why it didn't. 1.03. What's this down here? No. All right. Question there. StatCrunch. Oops. So we go back and do it again. Oops again. Oh, usually it works the second time. I don't know why. Failed 3 times. It's never done that before. Wait a minute. Maybe I've got a StatCrunch down here. There. You're looking at StatCrunch anyway, right?
Yeah, right now I am looking at it.
Oh, okay. Well, that's all we need. Oh, well, it gives you the p-value. When we did the hypothesis test, it gives it to you here. So that is the p-value. But let me show you the other way you can get the p-value.
But isn't that the p-value of the last question?
This is a different problem.
Yeah.
Okay. Close that out. Let's go stat, t-stats. Oh, we could do hypothesis test on this problem here, and it would give us the p-value, okay? But we can also do it this other way. It's a one sample with data. Well, no, this has got the wrong data in it here. I'm just going to do t calculators to show you how you can get this p-value, okay? It has nothing to do with the data over here on this left column, right? I'm just going into a calculator, and we'll give it our own data, okay? Stat calculators, t calculator. I'm going to say between, and the t value that we had that we were looking at We do have to know the degrees of freedom for this. So let me look in our problem here. Okay, our sample was 15 3-year-old boys. So N is 15, okay? So our degrees of freedom is going to be 14, N minus 1, 14 for our degrees of freedom. And our T value, we want between 1.03, 1.03 and negative 1.03. Do you see that screen up here? Where it's
Yeah, I do.
So I just said we got 14 degrees of freedom, so that tells it which T curve to go get. And here's the T values, because we're in a T calculator, so this is really T down here. So the probability that we're between minus 1.03 and plus 1.03, and we hit compute, is this number, okay? Our p-value is the probability that we're outside of that red region, the probability that we're in one of the tails. And we get that by 1 minus 0.6795, okay? So I'll put that in the calculator. 1 minus 0.6795 equals, so I get 0.3205 for our p-value, okay? If that's our sample that we got a t of negative 1.03. So this was our sample right here. What's the probability we got something more extreme than that? And you have to include either tail. So more extreme than plus 103 or more extreme than minus 103. And the answer is 1 minus this probability. And this thing's showing us the probability between. So the p-value is 0.3205. Go back to the problem. I got to reshare it. Stop share. Share screen. Well, that's not showing the problem there. Maybe this was, no, that's not the problem. Was this it? Maybe. Yeah, okay. So the p-value I got was 0.3205. And how many decimals does it want? It wants 3 decimals, so 0.321. Okay. Now we could have got that another way. We could have done the hypothesis test, and it would have given us that in the report, right? And actually we did that before. I think we, yeah. I can't remember if we did the hypothesis test on this problem or not. But you go into stat and t-stats, and then you have to put in the value for the null, okay, which here would have been 37. And you also had to put in, you had to state your alternative hypothesis. So you make sure that the HA said mu not equal to 38, okay? Because we're just testing, the test we're doing is just that it's that the mean has changed, that it's not 38. So that's another way you could have got P. Okay, so do we reject or not reject? We compare P to our significance value, which is 0.05. We do not reject because this is way bigger than 0.05. The other way you could see that is our t value was minus 1.03, so that's only one standard deviation, 1.03 standard deviations away from that proposed mean. That's not very far away from it. So we got a good probability that we would have obtained that value just by chance, okay, if that was the real mean. If it was located where we said it was, there's a good chance we'd get the sample we got. So we cannot reject. do not reject. There's no reason to believe that it's not at the significance level. That would be true. The other one says do not reject. Population mean is definitely this value. No, we don't know that it's definitely that. We just know there's no reason to believe that that's not it, but we don't know that it definitely is that. So B's the right answer. Check answer. Okay. All right, so suppose the sample consists of 30 boys instead of 15. Repeat the test, okay? So let's redo our calculation here. Let's use that other stat method here because we'll get T and P the same way. So I'm going to get back into StatCrunch. Make sure I got all the information before I get there because it's not going to preload it, okay? So 38 is the population mean. We got 37.2 for our sample. I don't know if S is equals 3. We may not need that. Okay, and N is saying now N is 30. N equals 30. Okay, and we're just redoing the test. So we'll go into StatCrunch. An error has occurred. Let's do it again. Let's go into StatCrunch. Error has occurred. Third time's the charm. Okay. Well, it's not wanting to go into that right now. I don't know why. What was this down here? That wasn't StatCrunch, was it? I don't think. No. I'm going to say stop share. Maybe I've got a StatCrunch somewhere else I can find. Ah, there's one. Good. We'll trick it. Well, well, let me select that there. Okay. You see StatCrunch now?
Yeah, I do.
Okay. Get out of this. I'm going to say stat, T-stats, one sample, and here I'm going to say with summary because we don't have individual readings. They just told us that the X bar was 37.2. We don't have the individual points. So T-stats, we're going to do the hypothesis. And this, let me do this because it's not showing you that there. Just make sure you can see it. Stat, okay, T-stats, one sample with summary. Sample mean was 37.2. Sample standard deviation, it told us that it was 3. Hypothesis test, sample size was 30 because they changed it, right? And mu was 38. It was saying country A was 38 and perform the test. That's all we need. So we say compute. So here's our new T-stat and our new p-value, okay? Our test statistic T equals minus 1.4606, and our p-value is 0.1549, okay? So go back in the problem. I got to share it again. Okay, and I'll just put, it says to 2 decimal places, minus 1.46, likes that, p-value it says rounded to 3 decimal places, 0.155, 0.155, okay? Do we reject or not reject? What do you think, Ruben?
I think we reject.
Okay, we do not reject.
Oh, do not. Okay.
The reason we don't, you can look at it 2 different ways, okay? If we just look at the p-value, to reject, the p-value has to be smaller than the significance level, okay? And the significance level is 0.05. We tested at the 0.05 significance level. So for us to reject it, we got to get something more extreme than 0.05. And more extreme means smaller. We need a lower probability that our sample would have hit there if that thing was true in order to reject it.
Okay.
We have a low probability. We got a fairly high probability that if it's true, that we would have got this value or worse, okay? So we cannot reject. Do not reject, so the population, let's see, so there's no reason to believe, or we have insufficient evidence to believe that 38 is not the population mean at this significance level. Okay, continue. Explain why the t-values and p-values for part A and B are different. Okay. A larger n causes a smaller standard error. Well, that's true. You get a better average so that the deviation between averages, if you went and got a lot of samples, okay, and measured the standard deviation between those averages, if your sample size is larger, if there's more that make up a single sample average, the averages themselves are going to jump around a lot less, right? They're going to be closer together. If I get a sample that I've got 100 and I'm average them, and I go get another 100 and average them, those averages aren't going to be as far apart as they would be if I only went and got 10 and averaged them, right? So a larger n causes a smaller standard error. That's true. The formula for standard error is the sample standard deviation divided by the square root of n. So if n gets bigger, the square root of n gets bigger, but we're dividing by that. So this standard error is that ratio. It's that value of that fraction. It's the value of the standard deviation divided by the square root of n. So the standard error gets smaller when n gets bigger. And that makes sense, right? Larger sample size, we can have more faith in the number we got for the average is probably going to be closer to the true average if we have a larger sample size. So we'll have less variation in the averages. Okay, so that means it's a narrower sampling distribution. And this says with less area in the tails as shown by the larger p-value. Okay, so let's see what else we got for smaller standard deviation. With less area in the tails as shown by the smaller p-values. Okay, so when we did the n equals 30, I don't think we can go back. Can we scroll up here? Oh, we can. Good. So at n equals 15, okay, here's our t and our p-value when our sample size was 15. Our p-value is 0.3. So then we redid the test, only now we're using an average of 30 instead of an average of 15. So we look at our p-value and it's 0.155. So when our sample size went up, our p-value went down, okay? And so, and also what happened to the test statistic, it got a little bit bigger, okay? So that makes sense. If t is larger, your p is going to be smaller. That's always going to happen, okay? Because it's saying you have less area in the tails when t is larger. And this happened because we got a larger sample size, okay? So back to the question, it says, explain why t and p values are different. So we had a larger sample, does cause a smaller standard error, okay? And we have less area in the tails as shown by the smaller p-value. So it's C. Does that make sense? Are you okay with that?
Yeah, I think I got it.
Okay. All right. 30 GPAs from a randomly selected sample are given in this table. Assume the population distribution is normal. The technician in charge of the records claimed that the population for the whole college of GPAs is 2.89. So that's our null value, 2.89. Now we're doing, it says a one-sided test, okay, which is actually simpler than the two-sided. But it says a one-sided test had previously been performed and the null was rejected. Use the data to find a 95% confidence interval for the mean GPA. Okay, so use the data to find a 95% confidence interval, okay, for the GPA. So a 95% confidence interval, let's see. Then it says if a two-sided test had been used, would the hypothesized mean have been rejected? So that's a good question, okay? So here's a case where they're showing you that you get different results, perhaps, when you do a one-sided test as opposed to a two-sided, okay? So it doesn't tell you which one-sided test was performed here. It just says a one-sided test was performed. Okay, so it wants to use the data to find a 95% confidence interval. So let's do that. We move this into StatCrunch. And didn't work that time, so I got to get it in there. Then I'll share it once I get it to work. I am in Chrome, so I don't know why I'm having trouble now.
You probably have the other StatCrunch page still open.
Oh, okay, okay. Are you seeing it?
No, I'm just probably wondering if that's probably it.
Oh, okay, okay. Yeah, the thing is, I can't see another StatCrunch page. Let me. I'm going to hit stop share here. There. Now share. Okay. go back to this and see. Now that's the problem. Yeah, it doesn't show another stat crunch anywhere. Let me minimize that. Well, no, you can't. You gotta. Yeah, it's not liking that for some reason. I'm not sure if I stop share there and start it again. And now I gotta select that. Not sure why that is. I tell you what, Ruben, we've been at this an hour and 40.
Yeah.
So I will do a part 2, okay?
Oh, okay.
And you don't have to be live. I'm going to make a note here. Let's see. I got a couple. I lost one of my other notes that I had. That's not good. I'm going to write down where I'm at. There, okay. I want it. So we're on 8 of 12 on homework 7. So I'll continue from there. I'll make another video where I start on this problem and do the rest of them, and I'll post it on Blackboard, a link to it, okay?
All right.
So keep messing around with it, all right? I'll be putting I've got some other videos I'll be putting up too.
In Blackboard?
Yeah.
Okay.
I've done several of these. I just got to go back and label them and figure out what's what and get them posted on there.
All right.
And so watch those. And then remember, there's PowerPoints under that Tools for Success that explain a lot of this too, okay? Be reviewing that. And I sent out an email. I don't know if you saw it, but we're not going to do the chi-square stuff now. There's still a homework for it, but you don't have to do that.
Oh, okay.
It is extra credit. So you
okay.
do it, and I'll count it as extra credit. So
Right.
with that, I'm going to get out of here. I'm going to try to cut the grass, I guess, while I still can. So have a great day.
All right.
Give me an email if you got a question, okay?
Okay. Thank you so much
You're
for
welcome.
the help.
Have a good one. Stop.